So let's take a look at average value of a function and see what this looks like from a calculus perspective, and also compare this to average rate of change and see how the two compare. So the bottom line is average value is saying if I have some graph, some function that's graph, say f of x, I don't know, we can even give this, say x squared plus 1. Oh, let's try that again, x squared plus 1. And I would like to know the average value on the interval. We'll go from 1 to 4. I want to know the average outputted value. Literally, what is the average output of this function between 1 and 4? And we're going to treat this a lot like we would treat finding like the average on a test, for instance. If we were to find the average on a test, we would add up all of our test scores and divide by how many we have. We're going to do this sort of in a more continuous fashion, where this time we're going to start from 1 and go over to 4. And we're going to add up all of the output values continuously from 1 over to 4. And then we're going to divide by the interval over which they were summed. So, more specifically, we're going to add up or sum all the outputs. So take the integral from 1 to 4 of our function with respect to x. And then we're going to divide by the integral. Oh, there we go. And we're going to divide by the interval over which we sum those. The more general formula for this, you may see this written as 1 over b minus a times the integral from a to b of whatever function we want to find the average value of dx. So this is what the average value is. And what this is going to output is literally, it's going to give us the average outputted value for this function. We can think about the first output here being down at 2, and then the highest output here being all the way up at 17. So let's see if we can figure out what the actual output value would be for this guy. So we're going to zoom out here just a little bit, maybe. Move this guy over. So 1/3 times add 1 divide 1/3 x cubed plus x evaluated at 4 and 1 equals, actually we'll come down to the next line, equals 1/3 times, I'm going to put in my 4, so 4 cubed over 3, 3 plus 4 minus 1/3. If I put 1 in, 1/3 plus 1, pull this up, equals 1/3 times what? 64 thirds plus 4 minus 1/3 times 4/3. And let's see if we can simplify this guy and get it going by hand while we're at it. 1/3 times 64 over 3. I'm going to make this 12 over 3 minus 4/9 as I multiply. This should actually work out decently well. 1/3 times 76 over 3 minus 4/9, which is 76 ninths minus 4/9, aka 72 ninths, which is 8. So check it out. We have an average value, if we come back up here, an average outputted value along this curve of 8. Like that is the average output from here to here, which makes sense. Like that makes sense as an average output. It takes a little while to ramp up and get going, and then we get all the way up to 17 pretty quickly, especially because if you think about the outputs along the way, at x equals 3, we'd have an output at 9. So that 8 occurs a little bit over halfway, and that kind of makes sense as an average output value. So let's think about how else we could think about average value if we kind of put this into perspective. Let's grab a different color and we'll get a clean sheet here. If we were to say take the average value on an interval, we'll say that we want to take the average value of a velocity function. And we'd like to find the average value of v of t on the interval from 2 to 7, just because. And we'd like to find the average value. We want to know the average outputted velocity. And we are given a velocity function. We could do that by taking 1 over 7 minus 2 times the integral from 2 to 7 of v of t dt. That would give us our average value. Whatever the function is, we take the antiderivative, plug in 7, plug in 2, and multiply by 1/5. Great. But let's think about what this actually is doing here. The antiderivative of velocity is really position. So what this is really doing is saying 1 over 7 minus 2 times, if the antiderivative of velocity is position, that's s of t evaluating at 7 and 2. This is the same thing as s of 7 minus s of 2 over 7 minus 2. That means that both of these two things are equal to my average velocity. This used an integral and the velocity function to get to my average velocity, whereas this guy, this is what we used before to get to average velocity. Change in position over change in time. That's exactly how we found the average velocity of a function, or average rate of change, way back when in the beginning of the year. Notice these two things, they're equal to each other. They're identical. One is just using the velocity function, whereas the other uses the position function or position curve to figure this thing out. So if you're ever in a situation where you're asked for an average velocity, for instance, the next question that you should be asking yourself is, what do I have? Am I given a velocity function, or am I given the position function? If I'm given a velocity function, I'm going to use my average value integral to find the average velocity of my given my velocity function. If I have a position function, I'm going to do change in position over change in time. Think about my units there. Even those work out. If this is position, say this is in feet, and time is in seconds. This is in feet per second. Right? Same thing happens here. I work backwards to position, that's in feet, and I divide by time in seconds. This works if you're talking about average velocity, average acceleration as well. Let's switch. If we're going to talk about average acceleration, find the average acceleration on an interval. What are you given? Are you given a of t? If so, 1 over b minus a times the integral from a to b of a of t dt is going to find your average acceleration. Are you given v of t? If so, v of b minus v of a over b minus a. Change in velocity over change in time. Think about there again, units work out. This would be feet per second again. That gives back to an average acceleration. And you might ask yourself, well, what if I'm given position? Well, then you're going to have to do some derivative work to get to velocity. But then once you have that, you're good to go, as long as you have that time interval. So we can use this idea of average value to get to an average velocity or average rate of change or average acceleration. And you'll see a bunch of examples in the work you do this chapter.